posted. It seems there's something going round in preparation for the Christmas season. But today, I just wanted to thank AIG and the whole committee that organized the mentoring program, and my mentor, Ria Brabham, who wasn't able to be here today, but I'm sure we'll be catching up soon on all of this. I've really found it quite useful, and today I'll just give you a quick snapshot of some of the work, or rather some of the challenges that a team I've been leading at the CSIRO have been trying to assess and better understand to help work with drill data in a way that's more efficient, but also geologically robust. So into a more digital world and moving into quantitative methods, we often have so much information, whether it's inherited as tenements passed hand to hand, or if it's inherited in bigger companies. But we often have so much information and too little time to really take a quality look at it, know what we have and what it really means. So we've been looking at tools that do this for drill core data, but to really understand it well, we have to understand the nature of the problem when it comes to geoscience. Typically, when you look at machine learning applications, it's quite a big buzzword now, and people apply it in a whole host of domains, and in geoscience, a whole host of applications. But machine learning really lends itself to large databases or data sets, things like Google and Facebook, or sorry, Meta, and so on, where you have an enormous, like trillions and orders of magnitude larger pieces of information that all can be integrated and related to each other. It also requires clean data, especially if you're going to go with a completely unbiased approach and just let the data speak for itself, chuck everything at the wall and see what sticks. You really need to know that your data is clean, that nothing is missing. Often if data or a certain data set is missing 20% of the values for all samples, you can't use that, and then you lose information. Appropriate relationships between data sets is really important. To get a full, complete picture of whatever it is you're trying to model or predict or apply, they really need to be independent or uncorrelated data sets, which can be sometimes challenging to really know ahead of time and work around. And then finally, you need balanced classes. So you need things that are going to be roughly equal. You need to know all the populations that you're training to find. You really do have a good balanced data set of each of those. You don't just have 10 of one and 100 of another, because you'll be very good at finding the 100 and the 10 will be completely non-representative. So in geoscience, not to cast too much shade, because machine learning definitely has its place and can definitely augment our practices, but we actually have relatively small data. There's a lot of people say, oh, we have big data, all these deep learning, but there's a lot of inherent biases in what we have, and certainly what you're sampling can be only 1/1,000,000th volumetrically of a mine site. Even if you add up all the drill holes and add up all of your surface samples, the volume you're actually sampling to represent this huge domain is quite small. So that can be a challenge and can be mitigated with knowledge, but that's a consideration, and there's bias. You also have missing values and noisy data. So whether that's below or above detection limits when it comes to chemistry, noisy data. I mean, we're dealing with these vast volumes where there's going to be heterogeneity at various scales. We talk about fractal geology, where you see something at the small scale and it scales up. And that applies to many systems and many processes, but not everything. And there's always entropy involved. Also, the data sets we use are rarely independent. So our proxies that we have for various data sets representing things of importance in geology, we often represent the same handful of things in geology with different data sets. So really knowing ahead of time what you have and what it's used for is important. And often we also are quite unbalanced. We have lots of great data on things that are of economic value or where it's easy to sample, but things often a swamp behind a trillion mosquitoes probably is not going to get the same sampling quality as something next to the road. as well as, in the middle of a giant batholith, you've got granite for miles. It's probably not going to get the same sampling density and perhaps not even the same analytical data coming out of the lab as something that is really important vein in a high strain system. So these are all considerations. They can all be mitigated, but they need to be properly thought through at the beginning. And then to add a little bit more to that, we have really defined problems in geology, mostly limitations from our slowly evolving knowledge and understanding mineral systems, conceptual modeling, and all that kind of thing. They are also big buzzwords, but essentially we're trying to represent what is out there that we can see and that we can try and comprehend. But it's very scale dependent. It requires time information, which can be a limitation for some machine learning and other data science techniques. It requires spatial awareness, which again, that has to be encoded, and it has to be encoded smartly, but it can be quite powerful. And then finally, predicting rare events. If you think volumetrically of the entire continent, how many world-class tier 1 deposits are in that volume? Probably pretty few, but you definitely really want to find those. So trying to predict those rare events can be a challenge. So not to scare you off, there, like I said, there's ways around it. So you have the predictive school of thought. It's a more supervised machine learning approach that can be used in geoscience. Yes, there are, throw spaghetti at the wall and see what stick type, where you just let the data speak for itself. But in geoscience, because of these issues, you really need to embed knowledge, but that has a lot of biases. And yes, it can be used, but it needs to be done very, very consciously and methodically. So if you don't know enough, or you don't have super confidence in how to apply that knowledge, you can take a more investigative approach with an unsupervised data science approach or exploratory analysis of your data to better understand what things are representing, where anomalies are, what an anomaly is, and so on. In this talk is supposed to be about drill data, so I'll stick to that from now on. Two of the biggest issues that I've seen is preserving relationships, whether that be relationships between data sets. So here you have a bunch of variables on the left. Each squiggle has, you can mark where the squiggle changes and say that there's a boundary. And if you can stack that up for a bunch of variables, then the boundary strength is higher. It's a little bit simplified in explanation, but you have many things contributing independently to a result, but that independence leaves a lot lost. When you talk about geochemistry, there's a lot of dependent elements. They're the building blocks of our minerals, and then mineral assemblages as well. Your abundances of those are quite important. So if you look at things independently, you're going to run into a lot of lost information. And same goes for looking at drill holes independently as well. You're losing that spatial correlation, which is so important for later processing. If you're going to put this into a 3D model, if you're going to use it to constrain anything else, you really want to know that cluster A in drill hole A is the same across the board, or is it different? Has something pinched out? Has something unlapped? You also have a probabilistic approach. So how do you know that the probabilities are going to go in together? Can you upscale, downscale? Having that uncertainty value will be quite useful. Compositional data as well, very important. We talk a lot about mineral systems, but in that you have compositional knowledge. So mineral assemblages, how do you represent that as an index itself? And then use that to track through the hole. And then finally, missing data, there's two types. This is the most frequent type. Maybe you have old drill core data and you've reanalyzed a few holes with something more powerful and modern. How do you make sure that it all goes into the soup? Because there's valuable information in that old stuff, and there's extremely valuable information in that smaller population of new stuff. So how does it all go into the soup? Doing that smartly is quite a challenge, actually, but there are ways to work around it. And also, if you want to go on a spot by spot instead of data set by drill hole basis, where do you pick a boundary? Well, you can look at one data set and then throw everything else out that's missing 20%, or you can also put it all into the soup and get a probabilistic trend and then use everything to contribute where boundaries are. So That was a little bit of a speed run, but I would like to say that there are tools to help you out there. They are being developed. There's several, and we are evaluating more and more every day. We are launching Data Mosaic 4 or C4, as I've now coined it, and we are looking for case studies as well to test this out and see if you've got a problem it can't solve and how do we fix that. Thank you.
Yeah, today I would like to share one of my passion around geostatistics and how I came into that with an hydrogeological background. So, and basically, why do geostats matter? So why do patterns and geostatistics matter especially when you are dealing with hydrogeology? So I'm going to present you a few examples. And here I'm considering 3 totally synthetic cases, but you can imagine that they represent an aquifer with shared hydraulic conductivity properties, but distributed totally differently. So on the left, we can see some kind of very noisy pattern. And basically, we've got random noise defining the hydraulic conductivity. In the middle, we have something a bit more organized. This is a realization of a sequential Gaussian simulation. And we can see that typically high values in yellow of hydraulic conductivity form some kind of clusters, and low values of hydraulic conductivity in blue form other clusters. And on the right side, we have some kind of very organized patterns. We've got some channels with higher hydraulic conductivity properties and a matrix that presents lower hydraulic conductivity. So why does it matter to characterize this pattern and recognize them? Well, if you to do something. Okay, so if you run some flow and transport simulations through these domains, here we are looking at, on the bottom row at some hydraulic head, so the water pressure, and we can think of that as basically having a flow from left to right of the model with some fixed boundary conditions on the left and on the right, and no flow on the top and the bottom. And we can see already the hydraulic head looks different. If we look at the velocity field inside these mediums, we can see that for in case 1, basically, we have lots of tiny channels with relatively high velocities. In case 2, the velocities are dominated at some locations, but already if we look at the scale of these velocities, they are already 1 order of magnitude greater. And in the case of specific channels, then we can see that, not very well here, but the high velocities are in these hydraulic conductivity channels, and the magnitude is even bigger. So yes, patterns really matter, especially when you want to do some predictions that rely on nonlinear physics. And if you look at transport at the outlet of the model, typically for the different case, you will see very different arrival times. So the fastest medium will be the third case, and the slowest medium somehow to let a contaminant go from the left to the right side of the medium would be the second case. So how can we differentiate quantitatively these different mediums? So we can start looking at 1-point statistics, which is basically looking at the moment. So it can be the mean property, it could be the standard deviation, could be some kind of percentiles, or we could also look at the distribution of the values. So what happens if we compute the mean and the standard deviation of the hydraulic conductivity? For the first case, you've got these values. For the second case, you've got the same values. And for the third case, you've got the same values. And if we look at the histogram, for all three cases, we've got similar histogram. So 1-point statistics, they give you some information about your properties, but they are completely unable to characterize the structure of the medium. So what happens if we try to consider 2-point statistics? So typically, with 2-point statistics, we are looking at the pairwise dissimilarity of the property as we increase the distance between these 2 points. Okay, so we can build what is called a semi-variogram to look at that, and it can be linked with a correlation. If we take a look for 3 cases, so for the first case, we see with the blue dots that typically we have a semi-variogram that is close to the semi-variance or the standard deviation of the model, and this is pure noise. So this is what we call nugget effect. If we look at the semi-variograms for the case 2 and case 3 simulations, then we can see that they are already a little bit different, but still quite similar. So how can we better discriminate between these models? Typically by looking at multiple point statistics, so considering at least 3 points that are used usually in a neighborhood, so as is connected to some kind of simulation node, and we can count the different patterns that can be formed, and we can look at multiple scales. And so if we consider 3 different cases here, that could be potentially what a multiple point histogram could look like. So here we have most representative patterns and with a number of patterns that are counted for them. So we can see that in case 1, it's very noisy. And for case 2 or case 3, we have different structures and counts on the patterns. So what is great? What can you do with multiple point statistics? You can really generate lots of structures and models. You can also complete missing information, possibly. And you can eventually also try to reconstruct geological maps from geophysical data. So here on the left, you've got 3 geophysical maps that are auxiliary variables and that you can use in coordination with some kind of informed geological map in a training image to try to reconstruct your geological map. So on the right, you've got a reference geological map which is still one interpretation. And on the left, the three realization here that can illustrate what you could produce using multiple point statistics. And with that, I'll stop here. And thanks for your attention.
This talk is going to be all about the Saltbush prospect and its discovery, which has really been a team effort. So I just wanted to thank the whole of the Great Boulder team, who a lot could fortunately be here tonight. I think a few got flights just to be here for me. So here's an image of the historical workings that you see at Saltbush. Taken back when we were doing geological mapping, and Saltbush is one of the projects. Saltbush is part of the Sidewall project, which I'll talk a little bit about to start with to give a bit of context for the discovery. So this is just the important information statement, basically saying that this presentation is not investment advice. So the Sidewall project is Great Boulder's main focus of exploration, and it's part of the Meekatharra Gold Hub. It's situated in the northern Murchison domain of the Yilgarn Craton. And as you can see from this image here, the tenements sit over here, which is just to the east of where Westgord's Paddy's Flat operations are. And these overlie the Meekatharra Ridgy Greenstone Belt. So Great Boulder has 2 main deposits in this area. So the first, which is our flagship project, which is Mulga Bill, which is situated here, and then Ironbark, which is just along this trend there. So ironbark is a bit more relevant to this talk. So the gold mineralization at ironbark is hosted in a mafic package associated with ultramafics. And it's worth noting that it's considered that this ultramafic package could be the eastern equivalent of the lithologies that host the gold occurrences at Paddy's Flat on the western side of the Pallelsil incline, which folds the lithologies over. But until recently, there hasn't been very much exploration along this trend. So the ironbark deposit, it was found using an auger program. And so since that was successful at ironbark, we decided that we wanted to do a larger scale auger program north and south of the deposit in the hopes of finding something else. And so that's what we did. The auger program was 400 meters by 50 meter spacing, and then we infilled that to 200 meters in selected areas. And the results of that were really quite interesting. And it picked out a number of different targets along the ironbark trend. And here I've got an image which are weighted sum heat maps generated in iGas. And on the left, we have arsenic and antimony. And on the right, we have silver, bismuth, copper, molybdenum, and tungsten. The left is kind of typical pathfinders that you find at ironbark, and the right are the typical pathfinders at Mulgaville. And as you can see down here, where Saltbush is sat, kind of both of these signatures are present, although the Mulgaville style sits slightly closer to the east, where we actually have a granite, and then the ironbark style sit more to the west, where you have the greenstone belt. And so we have this zonation of pathfinders. And we gave this data to Scott Halley to kind of look at, and he gave us some of his kind of conclusions about the regional mineral system going on at Sidewell. And so just to kind of provide this quote, he said that the combined auger coverage north and south of the ironbark has defined a hydrothermal gold system more than 14 kilometers long, an area equivalent in extent to the Paddy's Flat gold camp. At the same time that we were doing the auger program, we also went out and did some mapping and did some grab sampling. And down at Saltbush, where the historical workings are, we sampled quartz veins, and that came up with some pretty promising results. We also went onto WAMEX and found historical holes that were reported by ESSO exploration in 1986. And there were 35 RAB holes and 3 RC holes. One of the RC holes had 1 meter at 20 grams per ton. And so all of this information was really important because it provided us with the confidence to be able to go in with an RC rig at Saltbush. And so that's exactly what we did. So the first RC program was completed in December 2023. And as of October just gone this year, we've now completed 4 RC drill programs. And so the first program was really kind of initial test. Can we confirm that mineralization that ESSO found and explore around the historical workings? And that was successful. And it kind of showed us that the northern area may be a bit more prospective because there were high gold grades and there were more elevated pathfinders to the north. And so that's why for phase 2 and for phase 3, we really kind of extended further north. And it was in phase 2 that we started to realize that both the gold mineralization and the pathfinders, as you can see from this image here, were plunging down to the north. And so then in phase 3 and phase 4, we've kind of pushed further down as well, not just north, but deeper. And phase 4 was a program for infill of a resource estimate that's still pending. Yep. So just to talk a bit more about the geology now. We noticed straight away from phase 1 that the gold mineralization was associated with 2 sheared mafic lithologies surrounded by sheared ultramafic lithologies, which is very similar to the mineralization that we see at ironbark. There are quite a few differences between the northern and the southern area that we're still trying to figure out why there are differences. But for the northern area, we know that the gold mineralization is dipping steeply to the west. And as you can see, kind of over there, I don't know where the pointer is. And there's also a large komatiitic unit that kind of sits sort of on top of the mineralization to the west as well in that green, in the purple line. And you can kind of see how the structure is affecting the weathering profile over to the east. Yep. And then So just to show you what the chips look like, this is just an image from one of the chip trays that graded quite nicely, 24 SVRC002. So just to kind of walk through it, above 60 meters, it was that chromatiotic unit and some sheared ultramafics. And then we hit the mafic unit, around 63 meters, a little bit of silica alteration came in. We hit water at 66 meters. Then the rock became a lot more sheared into that sheared mafic unit where fuchsite alteration came in, a little bit of sericite and some quartz veining. But it wasn't until about 70 meters in this hole that we got the mineralization, which kind of came in with hematite alteration, and the quartz veining is a bit more laminated there. At 73 meters, there was really obvious pyrite, and the pyrite has a few different forms. It can be semi-massive, it can be vein selvage, and sometimes it's a little bit disseminated as well. So there's a few kind of structures, textures there that we know about. So that's the mineralized section. And then at 80 meters, we go back into an ultramafic kind of slither between the two mafic units. And sometimes this ultramafic slither is mineralized, only sometimes though. Where it is, you have pyrite kind of flooding the host, and a little bit of quartz veining as well. But that's not as important as the main mineralization just above. And then it goes into the second mafic unit at 87 meters, where the alteration really kind of drops out. There's less mineralization really associated with this lower mafic. And then we go back into the sheared ultramafics at 100 meters, where there's a lot of talc alteration, which makes it a nice end of hole. So in October just gone, our manager let us kind of organized a trial run of the Micromine AI grade copilot block modeling license. And so I just kind of had a go on this and kind of threw in the saltbush data, produced some kind of a few different models based on different pieces of data. And I generated this model here, which is based purely on gold and structure. And we actually ended up using this as an exploration tool, just to add one more hole into the drilling that we've just done on the most northern line. And so you can kind of see this hole here shown by the red arrow. So this most northern line, we've done a lot of drilling on it before, but we haven't really seen any evidence of the mafic lithology, and there's not really any gold mineralization that we've seen. So the question we've been trying to answer is, where does that mineralization go? And so we just used this model as like a specific drill target. It was suggesting maybe there's something here, so maybe we'll hit something, but we don't have the results, so I don't know at the moment. So if I'm wrong, I've just told a whole group of people that I'm wrong. Yes, so that's that. And then just to kind of summarize kind of what's next on the deposit scale, we want to know, where does saltbush extend to? How far north can we take the deposit? Was that AI block model correct or not? Can we do another program of drilling? And then on the local scale, going back to that auger program that I mentioned, we have this another auger anomaly of arsenic and antimony to the northwest of saltbush, which is again kind of a long trend of saltbush. So we kind of want to look back at that. Is there another pocket of mineralization there? And then on the regional scale, we really want to test this identified regional mineral system. How far does it extend? And so we've entered a joint venture with One Banner Pty Limited to explore further south of saltbush to try and do that. So even though saltbush at the moment is quite a small area, we're quite excited about it because it could be a part of something much bigger. And so that is, I think the whole team is excited about that.
I'm going to present about geology and microtectonics of boundary region of two different thrust sheets, Jajarkot Cliff and Karnali Cliff, located in the western Nepal. Background is the topography of part of our study area. This is the geological map of Nepal, where different tectonic units are separated by major thrust and fault. The thrust and fault are extended almost along the whole length of the Himalaya. This is the geology cropped in western part, where there are two different thrust sheet, Karnali Cliff and Chajarkot Cliff. They are separated by aerial distance of about 15 kilometer, but they have different lithology, metamorphic and stratigraphic characteristics, which is quite interesting. While reviewing the regional geological map of Nepal, we could find key difference here. In right-hand map prepared by Upeti and Lafort, there is a direct connection between two thrust sheets. However, in left-hand map, it shows the existence of autochthonous unit, that is Lesser Himalaya, between two thrust sheets. This controversy necessitated the investigation in this area. So we select the study area to cover these two thrust sheets and to see what the actual scenario is here. This is the digitized map of different researchers, that is for our study area. And we get really confused due to different interpretation by different researchers regarding tectonic boundary and geological unit. This also highlighted the need of detailed geological mapping in this area. We supplemented our investigation by preparation of generalized columnar section and petrographic analysis that was not carried out by earlier. As there was, the map was prepared in very small scale, around 1:500,000. This is the investigation route. First of all, we carry out reconnaissance survey route to select the detailed survey route, where we spent around 2 months, long time in the field. The area lies in the remote part of Nepal and has rugged topography, and it encountered landslide problem in monsoon season, which impacted our study as well. We carried out field investigation mostly by foot. And this is our team, where different members have different objective. This is the methodological approach where we carried out oriented sampling. The north in a sample was taken in field, which later get transferred to thin section. The preparation of thin section was quite difficult in our university, as after cutting the sample in a specific dimension, we have to prepare it manually to make it transparent for petrography analysis. During that time, many samples get destroyed. However, we were able to prepare 80 sample for petrography and microtectonic analysis. We prepared geological map and based on the local type locality. Unlike to map of Upreti and Lafort, we observe the presence of autochthonous unit in between these two thrust sheets, bounded by Jajarkot Cliff in the south and Karnali Cliff in the north. This Jajarkot Cliff is itself folded by syncline and anticline. This is the tectonic stratigraphy, where the major lithology of this autochthonous unit is phyllite and meta sandstone of low grade. However, the Jajarkot Cliff has lithological characteristics of quartzite, schist, and marble. The Karnali Cliff has kyanite grade metamorphism, and kyanite and garnet bearing gneiss is predominant. This is the generalized columnar section we prepared, and along with the field photograph and petrography. Similar for Jajarkot Cliff as well, and for Karnali Cliff, where there is orthonite and paranite. Up to kyanite. Kyanite is a key metamorphic index mineral, and plagioclase here indicates orthonisic origin. We also prepared metamorphic zonation mapping, where we observed inverted type of metamorphism. It is the chlorite grade metamorphism in the middle part of the autochthonous unit that gradually increases moving toward the thrust zone up to garnet grade. However, Jajarkot cliff itself is metamorphosed to garnet grade and Carnal cliff up to kyanite grade. It is quite interesting here. This is the sample point for we carried out microtectonic analysis. We analyzed for different geological unit and for major geological structures as well. We analyzed recrystallization feature where geometry of quartz grain represent the temperature of recrystallization during deformation. We observed different type of recrystallization there, but predominant is high degree of recrystallization, and we summarized it, and we found the rock are recrystallized to high temperature, most of the rock, and this autochthonous unit has a low degree of recrystallization around 300 degrees Celsius, and it increases while moving toward the thrust sheet, but the rock of Karnali cliff and Jajarkot cliff are recrystallized up to 700 degrees Celsius. We also analyzed garnet porphyroblast relationship, where we observed pre-tectonic to post-tectonic type of garnet. This orientation of inclusion represent the growth of garnet before deformation in pre-tectonic, during deformation in syntectonic, and after deformation in post-tectonic garnet. We also correlate with the tectonic unit, where we found in Karnali cliff, majority of the garnet are of pre-tectonic nature, and in Jajarkot cliff, there are different type of garnet. The microfold is observed in different section that represent grain scale deformation. It can be correlated with the outcrop scale fold. It represents north that get transferred from as a oriented sample, and this represent north direction, and we observe here west trending fold. It can be correlated with the regional geological fold as well. The east-west trending fold in Himalaya indicate the fold are formed after the formation of Himalaya. There are many shear sense indicators like asymmetric quartz body notch, mica fish, shear band cleavage, and orientation of garnet inclusion that most of them represent top to south sense of shearing, indicating the tectonic block moved from north to the south. We also compared the recrystallization observed at the southern part of study area with other thrust sheet of higher Himalayan affinity. We also found similar nature of recrystallization. Thank you for providing.